Hello, I'm Mr. Steele, and to be fair, I'm only doing this video because it bothers me that there's one lesson that doesn't have video solutions. In truth, I don't think you need these video solutions. I anticipate you probably don't. I also would expect that if you took Calc Lab, you definitely won't access this video. And if you didn't take Calc Lab, obviously schedules are oftentimes outside your control, but this would be a good opportunity for me to kind of reinforce, you should have kept up with a little bit of the work, or you should have at least referenced that work once in a while, or maybe popped it up over the last few days of winter break. But yeah, honestly, I'm not doing it for any of the reasons like there, because if I wouldn't be making the video. I'm doing it because it bothers me that there are no video solutions for this particular lesson. So in a sense, this is about satisfying my OCD more than it is about any of you or about any sort of principled stance. In fact, it's stronger than a principled stance. So yeah, I'm going to work through this video because it bothers me and annoys me that there's something missing. So yeah, we're going to talk about anti-differentiation. The lesson title sort of shifts around. I have this one called Undoing Derivatives. It might be called Anti-Derivatives. It's day one of our sort of backwards differentiation unit, or Neutate Narrowfed if you were in Calc Lab, but if you weren't, that's okay, because that term isn't even real. So I'm going to work through the problems as I always do, and then link them on the PDF. I think I'm doing about 2/3 of the problems, just because most of these go pretty fast. I'm not going to be as expansive as I think I probably have in some of the other ones here. I really want this done, but also it's freezing in my house right now because I didn't have the heat running while I was at school. Today, this is the day that we go to school, the staff members attend school, but the students don't, right after winter break finishes, and it was now 2024. Geesh. Well, go figure, it's 2024. But in any event, this is a good enough use of time, and then I can go and observe my Tuna Fish Tuesday as soon as I'm finished. So yeah, here we go. Beginning with question number 1, and I think I'm doing 3 of these for this first section's problems. Effectively, you're asked to find 2 potential functions with each given derivative. In a sense, this is to, 1, have you practice anti-differentiating, and 2, to have you reinforce the idea and meaning behind having that constant of integration at the end. So this is not a situation where you'll put plus c at the end, because we're supposed to find 2 potential functions. Technically, that would just be 1. Yes, it represents many possible, but you have to write 2 separate values of c. So let's see what we have here. So first of all, our goal here is we want 2 potential functions with each given derivative, and since we are given f prime of x, that means we're effectively trying to figure out what are some functions f of x that have this as its slope function, or as their slope function. So if you wanted to, one way you could think about this is to use the notation for an indefinite integral. That's the same question we're asking here. We want to know what function has derivative 3x squared minus 1 over x. And there's, these are pretty straightforward ones. I'm thinking you probably recognize, in fact, here, you probably recognize 3x squared as the derivative of x cubed. Like, in a sense, that makes sense because that was kind of your first power rule. That was like baby's first power rule. So you probably have that one handy. And then the second one right over here, 1 over x, is a little bit tougher, but this is the derivative of ln of x, but we're going to have to make a small adjustment. So a couple different things to hit here, though. First of all, what could we do here? We would say that this is equal to x cubed, and then minus, and then we'll have the ln of x. And then it asks us to write 2 separate functions that have this. So in your mind, you might think, okay, well, cool, 2 separate functions, we just need different constants. And in fact, we could say this is one of those functions. We could just say, there's one, we got one. And in fact, we could, because that includes the constant as 0. You could also choose, of course, any other constant. So for me, again, if you really knew me, you would know I tend to choose 42 as my constant. And I am 100% going to be exactly who you thought I was. So I'm going to put that in there. So at this point, you're usually like, cool, I got my answer, that's great. But this actually is incorrect, or it's not completely correct. That's probably the better way to put it. The reason it's not correct has to do with the natural log function. So in the rule you were provided in class, probably without a whole lot of context, just because there's a heck of a lot going on in this lesson for us to go through the minutia of all this. But effectively, you need an absolute value around the argument of the natural log function. Or else you need to guarantee that the argument is positive. And you might be willing to sort of submit an argument of like, nuh-uh, I don't want to do that, in which case I'd say that's not a very good argument, but I get where you're coming from. That's sort of weird. Why is that there? Especially if in your brain of brains, your brain's going to be orange today. No, it's always called gray matter, right? Let's do gray matter. So in your brain of brains, it's odd brain, that's okay. You're like, it's a tree. No, it's a brain. That's a brain stem right there. Nice try. In your brain, you're probably thinking to yourself, well, wait, the derivative of natural log is equal to 1 over x. Why does it not go backwards that perfect way? See, this is what you get on the video solutions. I get to talk about all those questions that you have in the back of your mind. You're like, huh, that's weird. And if you're inquisitive and curious, I will help address that. Well, the reason for this actually has to do with domain. Sort of a weird thing to think about it, but it has to do with domain. Effectively, since we don't know exactly what this antiderivative expression really represents, effectively we actually have to cover a couple different possibilities, because the function 1 over x, here is a quick little rendering, artist rendering of 1 over x. 1 over x looks like this. Actually, I'm going to make one little move here. Let's see if it'll let me. It will not. Thanks a lot. Thanks for your help, computer. Computer, let me select the thing that I wanted. Okay, so in any event, 1 over x. 1 over x looks like this. The reason I bring this up is that 1 over x has domain, and that's not official, we'll go with it. It has domain, x is an element of negative infinity to 0, union 0 to infinity. So keep that in mind. Now let's contrast that with the very similar ln of x. Well, ln of x, which you hopefully know the general graph for, although judging by ESQs over the last several years, people tend to not hold on to this particular one, ln of x looks like this. ln of x has domain. X is an element of 0 to infinity. And if you're looking at this going, well, okay, cool, thanks for the domain lesson. That's exactly what I wanted to do with my afternoon. But I would point out that this explains exactly why there's an issue. The ln function, which has a certain derivative, is only defined for positive arguments, or positive x values. The function 1 over x is defined for both positive x values and negative x values. We have a little bit of a discrepancy there. And so what we do, in order to make sure that this works okay, and to make sure that there is, I want to say fidelity is the right word, that there's that connection, they're loyal to one another, they follow naturally from one another, we ensure that no matter what, we can spit out values from that antiderivative, that function that has that derivative, by putting absolute values around the inside. Because here's the thing, if you slap absolute values around your ln function, obviously this will change the domain, but then you'll get the other side as well. You'll get a reflection across the y-axis. So there would be your adjustment. So really small thing, really tiny thing. I definitely would call it minutia. Sometimes it doesn't even make a difference in your answer. We're not even going to worry about it. We might just add it without taking away a point. But this is one of those rare opportunities where I can take an extra 3 minutes and really dive into what this is necessary for and why it's there. And there's your reason for why it's there. It's to make sure the domain of 1 over x matches the domain of the function with that derivative. And the only way that that would be possible is if it was ln of the absolute value of x. So nice little factoid for you to kind of go with. The more you know. Dun, dun, dun. The second problem we're going to address, I always get really excited when I say the first part. The second problem we're going to look at is, again, we're looking for two potential functions with that given derivative. I'll be a little bit more fancy, I guess, on this one. Choose some different constants, maybe. But we have h prime of t is equal to p double prime of t minus 1 over t squared. Now, this one definitely feels to me like there's a little bit more going on here. So just like last time, I'm going to focus on sort of having the two different colors here, just because I think that helps a little bit. So in the purple corner, we have p double prime of t. And in the, we'll call it the red corner, I think this will work okay, we have 1 over t squared. But I'm going to be clever here. Basically, I'm going to be clever, and I think it might help to think of this as t to the negative 2 power. Just a shot. If this doesn't work for you, cool. Again, we don't know the we know the anti-power rule. Heck, this is definitely the right choice. What am I talking about? Definitely do this if you can't just see it. So as far as pieces, though, let's start with what we know. So we're asking ourselves the question, what function has derivative bleu? So in this case, bleu is p double prime of t. So we're asking, what function would you take the derivative of and get p double prime? Well, I'm going to hope that it's pretty obvious. Pause for laughter. Laughter never comes. Continue forward. It's going to be pretty obvious that p prime is the function whose derivative is p double prime. So I'm just going to write p prime of t. We don't know what p is, we don't know what p prime is, we don't know what p double prime is, but we know that that's how we'd represent its antiderivative. So we'll go with it. As far as the second one, this can be a little bit tough, but we do know the anti-power rule. So remember, the anti-power rule says if you have the integral of x to the n dx, that's going to be equal to 1 over n plus 1 times x to the n plus 1, and then of course plus c, but we'll set that part aside for here. So in this case, like again, there is a restriction here. Of course, we know that n is not going to be equal to -1. If you're like, wait, why? Because of that. But we know that. In this case, n is -2, so we're good. So just kind of following this rule until you can kind of see it, we're going to have 1 over -2 plus 1 times x to the -2 plus 1. So cleaning this up a little bit, which I'm going to do, because why not? Obviously, we have p prime of t here, but then we also have what appears to be minus. We're going to have 1 over -1 is -1, and then x to the -1. And I'm going to go ahead and just switch to a single color here to clean this up. What that's going to amount to is p prime of t minus a -1 over x. So there is one of our functions. This is one potential version of h of, oh sorry, I put x in there. It's supposed to be t, isn't it? Spilled the tea on that one, folks. Let's fix both of those. Actually spilled the tea. It'd only be if like we talked about it separately, then I would, and like spreading rumors about it, like, oh, he's not careful. And so I can't drink tea, so maybe that's part of the problem. So basically there is one h of t. Remember, we're supposed to have two though, so keep in mind there's one option. As far as the second option, I don't know. I'm just going to add a different constant. P prime of t plus 1 over t plus, and let's go with pi to the 4.2 power. There is another function with a constant. So there we go. So again, in here, just kind of thinking abstractly or symbolically. It's almost symbolically, I guess, to call it p prime of t. And then for the other one, using the anti-power rule. Question number 4 then brings us in to look at not the hardest function whose derivative we might be trying to work backwards from, but there's definitely some awkwardness on this second term here that we're going to have to address. So as far as pieces, as we've done before, I'm just going to start with the first ingredient. We have 89. The function whose derivative is 89 is clearly aligned with slope 89. So I'm just going to put 89x in there. So basically 89x prime will give us 89. So that will be part of our answer. And now, yeah, okay. Now we got to address, as I say, address the elephant in the room. But it's not really an elephant. It's just a cosine function with some extra stuff, with some extra bells and whistles. So in here, what I'm hoping you notice, and again, these are designed to get you into the idea and to think about it a little bit. This isn't where we'll land eventually when we figure out something that's called the anti-chain rule. But what this is an opportunity for you to see chain rule in action. You see that there's a function inside of another function. It's just like tucked in there, turducken style. So you're like, wait, there's an x squared in there. You're not supposed to be here. Well, yeah, but everything's okay. We can still have a derivative from that, assuming that the derivative of the inside is outside. Or more technically, that a scalar multiple of the derivative of the inside is on the outside. So ask yourself the question, what is the derivative of x squared? Well, the derivative of x squared is literally 2x. So effectively what we have here is we have cosine of x squared times x squared prime. And in fact, that points us in the direction of the chain rule. This is definitely something involving the chain rule, or at least our derivative resulted from the chain rule. So what I'm thinking is, first, on the inside, we will have to have x squared, because that's what produced the 2x on the outside. As far as the other part, we ask ourselves, well, what function has derivative positive cosine? Like, what do we know that differentiates to positive cosine? And I'm hoping it's pretty positive in your head, or that you're positive that it's sine. So in a sense, what we have here, aside from like these things being lined up really poorly, visually speaking or vertically speaking, we have 89x's derivative added to sine of x squared's derivative. And where this is going to lead us will be our two answers here. We're going to get 89x. Actually, I'll write this with the appropriate colors. What's wrong with me? What's wrong with me? We'll have 89x plus, and then we're going to have, it looks like sine of x squared. Now, of course, we get two different answers. I'm going to put plus 42, and then for the other one, because I have a shtick, and I'm going to stick to it, let's go plus 42 e to the 42 power. So there are our two functions. Now, if you're looking at this and you're not distracted by my weird constants, you might ask yourself the question for a moment, like, wait a second, like, does that actually work? Did we do this correctly? Well, we can check either one of these. Let's just differentiate 89x plus the sine of x squared. I'll ignore the constant here, and let's see what we get, because we should just get 89 plus 2x cosine of x squared. Well, pretty straightforward. The derivative of 89x is 89. And then finally, for sine of x squared, that one does require, of course, the chain rule, as we've talked about before. So what I'm going to have here is I'm going to have the derivative of the outside function, which is cosine, of the inside function times the derivative of the inside function. We'll clean this up a little bit. We'll get 89 plus x squared's derivative is 2x, so 2x cosine of x squared. And of course, what do we see? Do you see what I see? I see a derivative that matches on the line at the top of the very page. It does what it's supposed to. So it looks like we did our job. Good job, us. Hooray. We did it. There's 4. Okay, next we're moving to question 6, and I'm just going to not lie to you. This is the same thing as what you're doing before, except in this case, because we framed it as an indefinite integral, we actually just want the specific family of functions. We want plus c in this case. This is the one where we definitely need plus c. Now, I didn't choose all of these. I think some of these are really straightforward to work through, and I think they're good exercises in general. Like, obviously, in a perfect world, you wouldn't be using this video. You'd be doing it yourself with a little bit of confidence, and then you'd check the written solutions afterwards to confirm if you did it right, only consulting this if you really needed help. But obviously, feel free to click on and watch if that helps you develop the skill a little bit more strongly. So I tried to choose ones that, as I was saying, I tried to choose ones that were a little bit trickier, had some element that I thought was interesting. In this case, I think the second term in the integrand of this particular indefinite integral is interesting. So let's look at the individual pieces. So the first move I'm going to make here, and this isn't necessarily the same move every person would make, but this is definitely the move I'm going to make, is going to be to use one of our properties. Like, I don't know that we necessarily address those properties just yet, but the properties do hold. You can separate this effectively into 2 separate little integrals. We're going to do the integral of 17e to the t dt. Now, that might look a little bit tough, but please don't phone home. You know, ET joke and whatnot. Yeah. No, that's totally current here in the year 2024. Okay, maybe not. And then the second one, we have 13 over the cube root of t. But I know that that's going to take a little bit of effort to get there, so I'm going to start sort of whittling it down. 13 over the cube root of t is 13 over t to the 1/3 power. And then taking that one step further, that's going to be 13 times t to the negative 1/3 power dt. Now, to evaluate this, we're going to have to take care of that one, and we will in just a second. But first, I do want to take care of 17e to the t. This one's antiderivative will be 17e to the t, and of course the reason for that is the derivative of an exponential function, just the basic power, is just that exponential function. So the derivative here would be 17 times the derivative of e to the t, which is 17e to the t. So that one's good to go. We're in pretty great shape. On the second one, again, assuming that you're able to convert it from a radical into power, like you're ready for the power rule, as well as, I guess, the scalar rule. I guess I should pull that out in front. We'll pull the scalar out. When we go to do the integral of t to the negative 1/3, let me just remind you once again that we're using the anti-power rule here. If you're a rules person, you're pretty deep in math, so I imagine you are a little bit of a rules person. That is, you do multiply by the scalar 1 over the power plus 1 times x to that power plus 1. So I'm going to do exactly that. So my power is negative 1/3. So I'm going to multiply 13 by 1 over negative 1/3 plus 1. And then we'll have up here t to the negative 1/3 plus 1. And let me just go ahead and take care of it right here for the moment. Negative 1/3 plus 1 is 2/3. So effectively, there is our antiderivative part. The only thing I'm going to tack on is a plus c just to make sure that I don't forget it. This is an investment in not forgetting it. Now finally, I can clean this up a little bit further. Negative 1/3 plus 1 is going to be 2/3. And we have 1 over 2/3 out in front. So as a heads up, if this doesn't necessarily jump out at you, the way that you handle 1 over 2/3 is that's just a division problem with a fraction. You're dividing by a fraction, so flip it and multiply. This will give us 13. Actually, I'll use the colors better. This will give us 13 times the reciprocal of 2/3, which is 3/2. And then, of course, we'll be right back to t to the 2/3 plus c. And, of course, we still have 17 e to the t plus all that. Now, of course, we were technically correct already. We could stop right here since we aren't expected to, simplify your answers or write them in a particular form. Again, on the AP test, like again, in a perfect world, you would. But for this one, we can clean this up just a little bit further. This will be 17 e to the t plus 39 over 2 times t to the 2/3 plus c. And now if you were dead set on rewriting that middle term as a radical, like since it started with a radical, I mean, hey, more power to you. I admire your guts, like go for it. But I'm not going to do that. I'm just choosing not to do it since it's not required. And the last thing I'll say here, and just to kind of point it out, is that it's really easy to forget plus c. A lot of people forget plus c, so don't be one of them. Like, be better. Be better. The next one we're going to look at is question 7. This one doesn't really need to be addressed, but I just wanted to bring it back as kind of a quick throwback. This one's probably going to be less than a minute. I just wanted to remind you how we handle that over x, that natural log one that's in there. So just as a reminder, the way that we handle this is, of course, we've got two separate pieces. We want to look at first the function whose derivative is ln, or 11. 11 sounds like ln. I got ahead of myself. The derivative, or the function whose derivative is 11, is of course 11x. Any constant's antiderivative or indefinite integral will be a linear function. And then we've got this guy, plus 5 over x. So to help with this one, the first thing I'm going to do is I'm going to rewrite it as an indefinite integral. This will be plus 5 times the integral of 1 over x dx. And I'm hoping that's enough for you to see it. The integral of 1 over x dx is the natural log function. But remember, we noted that domain forces us to include absolute value around its argument. So effectively, we'll have that. We'll also have the 5 out in front. So we're adding 5 ln of x to that. We'll have 11x in addition, because we were adding that in the beginning. And then in your mind, you're like, yeah, it's done. But nah, it's not done. There's a problem here. We, of course, don't forget any parts. Well, we forgot the plus c. Well, we temporarily forgot it, which is the same thing as prepping for remembering. So I'm happy that we got to it. There it is. There's the function whose derivative is given by 11 plus 5 over x. So just don't forget the absolute value here. It's such a simple problem. It feels like the kind of thing that you should be expected to remember. The next one we got is question 9. So I'm thinking there's a couple more in here. So for question number 9, this is another one that has that issue with the denominator. It's radical. It just kind of looks a little bit funkier. Oh, excuse me. Yeah. I'm tired. First day back on the get up at 2 schedule. So in this case, we have that f prime. So we have it represented sort of abstractly or just symbolically. So what do? Well, this is another one of those situations where I think splitting helps a little bit. So I'm going to do exactly that. First one, I'm going to do the integral of 1/5 f prime of t dt. It's a lot of t in here. It's like I've walked into a boba store. And then finally, we're going to have that second one. And it is 21 over square root of t. But I'm going to, just like before, rewrite this as a power. So I'll rewrite it as 21 times t to the negative 1/2 dt. And now with those two pieces in place, we should be able to evaluate this one. In a sense, we've gotten it out of that awkward radical expression. And now we're into the mode where we can kind of see the structure. We can recognize the anti-power rule or one of the other ones that are out there. So I'll start with the first part. So obviously we have a scalar of 1/5. We have to answer the question, what function's derivative is f prime of t? And I think that one's pretty trivial. It's just f of t. Because the derivative of f would be f prime. We're looking at an f prime. There's nothing on the inside except t, so we don't have to worry about like anti-chain rule type stuff. We're covered nicely. The next one, though, could be a little bit like stranger. Could be a little awkward. So we have the scalar once again. So I'm then going to multiply by 1 over the power plus 1. So we're going to have 1 plus negative 1/2. And then we'll have t to the 1 plus negative 1/2, which is positive 1/2. Last but not least, wither plus c. So now this is technically our answer. We could stop there, but I'm going to assume that you have a little bit of self-respect. So we're not going to stop there. Instead, I'm going to write this thing out. I'm going to have 1/5 f of t. On the next part, 21 times 1 over 1 minus 1/2. Well, 1 minus 1/2 is 1/2, and 1 over 1/2 is going to be 2. So this whole thing is 2, and if that whole thing is 2, we get 21 times 2 is 42. Nice. And then, of course, the t to the 1/2 was well reasoned. Nice job. Lastly, we need plus c, just because we need to make sure that we have all possible solutions. And if you don't like that, I was going to say take it up with Leibniz, who died a long time ago. But I was going to say if you don't like that, well, that's just the burden of proof that we're looking for here. So there we go. Okay, number 10, is that right? Oh, dang, 2 more. I'm exhausted and starving right now. Huh, it's 4:30. It's because I didn't eat enough. And also, yeah, I got to school today, and I went to take the cheese out to make my daily quesadilla, which is the only thing I've eaten for lunch for like a couple years. And my cheese was fuzzy. Yeah, you want your dice that hang on your like rear view mirror to be fuzzy. You don't want your cheese to be fuzzy. It's just not ideal. So yeah, I didn't have much for lunch. But this one, there's much going on in this problem. So I'm just going to lay it straight with you. There is a technique that you learn in Calculus BC that can technically attempt and attack this particular problem. That technique is known as integration by parts, and for all intents and purposes, it is the anti-product rule. Having said that, I don't feel like it would be a good move to even learn integration by parts for this particular problem. I think that this problem is sort of its own thing. This is a sort of like fortune hath smiled upon thee kind of problem, where you just look and you see all of the right ingredients to capture a particular rule. I guess that's the way that I'm going to look at it. So what I want to highlight here is, yes, okay, if you want the spoilers, this is about the product rule. This is 100% something that comes from the product rule. But having said that, like the product rule produces 2 terms. You know this, right? The integral of f times g, the derivative of f times g is f prime g plus fg prime. So one derivative, one regular, added together. Well, that's what this is as well. It's just a little bit tougher to see when you first look at it, because it kind of blitzes you with just like, rah! Like there's just a lot going on here. There's multiple terms. It doesn't look like an obvious technique unless you are comfortable with the product rule and you know differentiation really well. So to kick things off here and just start it off, what I noticed first is that each of the 2 terms here, you could like almost imagine like a line down. I'm not going to do it, but you could. But I noticed we've got 2 polynomial terms and we've got 2 trig terms. So let's inspect each of those. If we look at this, we have 4x to the 3rd and we have x to the 4th. Well, do we know a relationship there? Yeah. Oh yeah. The derivative of x to the 4th is equal to 4x cubed. Like exactly equal, by the way, too. Not even just like, oh, well, it's part way there. Oh, if x equals 7, no, it's like exactly equal. And likewise, we have the same relationship over there. We have what looks like tangent of x and secant squared. And, well, I don't have a better way to put it than just that tangent's derivative is equal to secant squared. So we also have those relationships. And then making matters even more convenient for us, I think that's probably the right word, convenient, x to the 4th derivative and secant squared. Like, if we look at those 2 pieces, we see x to the 4th and secant squared paired up right here. And on the flip side, if we look on the other one, we have 4x cubed and tangent of x. Those 2 are paired up right here. All of this is helping us sniff out the product rule. I had too many jalapenos last night and didn't take my Claritin this morning. And I'm a little snifflier than I should be. I sense the product rule. So at this point, I think it becomes pretty obvious where to go from here. It's sort of up to you, but effectively, like we know that the product rule comes from 2 original functions and their derivatives show up. So the question is, what are our 2 original functions here? Well, tangent and x to the 4th. So based on that, what I'm thinking is our original function would be x to the 4th times tangent of x, and then of course just plus c, because like we should probably just take care of that right now. And here's one of those spots where I'd point out that if you're not sure that you did it right, if you're like, oh, I don't know, it looks pretty suspicious, or sorry, let's use modern terminology, that looks pretty sus. Sussy? Sus. I'm pretty sure it's definitely sus. If that's the case, just like go differentiate it. Like, I'm not going to tell you have to do this every time and like pretend like you're supposed to check your work every single time. But just try it. The derivative will be the derivative of x to the fourth times tangent of x plus x to the fourth times the derivative of tangent of x, and then all plus the derivative of a constant, which is 0. That is this. We did it. We did it. That was what we were aiming for. And why did I erase that? Keep it around. So there you go. This one, product rule is definitely your way to go. This is going to bring us to the final problem in this section. I think it's the final problem. I'll have to check in a second. And I'm just going to be honest. This one looks intimidating. I would say this is probably the most difficult problem on this page. I think there's just a lot going on, and I think the structure is pretty challenging. Having said that, I think that approaching problem 12 in isolation might actually be sort of your downfall. I would say that it's important to kind of think in the large picture, and in particular to think about the problems that are around this particular difficult problem, and think about or consider whether or not they might be in conversation with this one. What I mean in particular is question number 10. Question 10 was all about recognizing the structure of one of our big differentiation rules and then sort of looking at the structure of each individual term to recognize which piece comprises the original product. Question 12 is most definitely informed by that approach, except this time we don't have a pure product. We have something with a bunch of crunchy stuff in it minus another something with an even more crunchier set of stuff in it, all over something to a power, and a power in particular that features a 2. What I'm hoping is that your brain is willing to conjure what we know as ye olde quotient rule. Ye olde quotient ruling? I don't remember how that technically goes. So the quotient rule, again, not to be confused with L'Hopital's rule, which is a totally different thing that just sort of has vague resemblances to it. The quotient rule says low derivative of high minus high derivative of low all over low, low. So effectively, that's the structure that I am theorizing is in play here. I think we're seeing the result of the quotient rule. That's my thought. That's my plan. That's what I'm going to do. If it doesn't work, well, then all of calculus is broken and my intuition is bad. And how did I solve it before I wrote this problem set? So in any event, we're going to look at it this way. So now from here, it becomes sort of a challenge. Like, okay, well, fine. I recognize it's quotient rule, but how do I find the individual pieces? I'm going to be smart about this. I'm going to start with the pieces that are most distinctive. The denominator is super helpful in the quotient rule because the denominator has the original function g. It just happens to be squared. So in this particular case, I'm going to look down here. And I'm going to reason out that in order for this to be the quotient rule, e to the 2x to the 5th is going to have to be equal to our g squared. Well, think about that for a second. If you want to figure out what the function g is, and again, we're going to set aside like scalars and stuff for the moment. Maybe we'll have to fix it later. I can just effectively square root both sides. And although this isn't perfect, you can pretty clearly reason out that g is going to be equal to the square root of that piece, which is e to the x to the 5th. So that's actually a huge help. What that tells me is this whole thing is going to eventually be equal to something over something, and then plus c, of course. I just want to make this look clean. So eventually this will be our answer. And what we've just found, I would submit, is that e to the x to the 5th is going to be in the denominator. Now, it is possible this could be negative. We'll check that afterwards. But for the moment, that's a huge move. We have g taken care of. Because also helpful is that since we've just gotten g taken care of, well, we actually can now isolate some stuff here. So if that's g was e to the x to the 5th, then everything else we see up there is going to end up being f prime. So effectively, we have f prime right there. You could say f prime of x is equal to 7 cosine of 7x. Now, in this case, I'm going to be pretty clever. If we know that 7 cosine of 7x is the function's derivative, well, that's just asking us to anti-differentiate just like we've been doing, right? Well, that would mean that f of x would be, sort of by the unchain rule, like we're seeing the chain rule in place. Well, the inside's going to stay the same. It doesn't change when you use the chain rule. And then what function has derivative cosine? Well, it's going to be sine. Sine's derivative is cosine. And then at this point, you might ask yourself, well, is there a scalar out in front? And that is a good question. What a great question. Great job, like disembodied voice in my head. Is there a scalar out in front? Well, let's take the derivative here. If we differentiate sine of 7x, we're going to get the cosine of 7x times the derivative of 7x, which is 7. So no, there's not. That's just our function f of x. And since f would be what goes in the numerator, this means the numerator will be the sine of 7x. Now I submit that this is our answer, that we've done the job, we've put in the work, we are ready to call it a day and we've done the work. But what if I'm wrong? Like, right, that's a distinctive possibility. What if I'm wrong? What if it's supposed to be a negative sign somewhere and I just messed this whole thing up? Well, let's see. Like, how can you ever check such a thing? Just, to quote Nike, just do it. Like, let's just take the derivative. Low d high, and I'll worry about the actual differentiating later. Minus high d low. Sorry, it takes a little while to go, and I kept a really brisk tempo on that song. All over low, low, quotient rule. Okay, so there it is. There's our potential function differentiated. And now let's see what we get when we actually simplify it. So first and foremost, that denominator will be e to the x to the fifth all times 2, which is e to the 2x to the fifth, which matches up. Good job, us. For the first part over here, let's do this with blue. Actually, do it with the color I haven't used, navy blue. Sine of 7x's derivative is 7 cosine of 7x. So that first term is going to be 7 e to the x to the fifth. I'm just kind of cleaning it up a little bit. Cosine of 7x. And then last but not least here, we're going to be subtracting sine of 7x and times the derivative of e to the x to the fifth. Well, the sine of 7x is going to stick around. The e to the x to the fifth will be e to the x to the fifth, all times the derivative of x to the fifth, which is 5x to the fourth. And, well, that's exactly what we had up there. So we did this correctly. So good job, we did it. There was no negative sign that was missing. That is always a possibility, although that'd be pretty cruel of me to do that, but we got to our piece. So good job, us. Nice work. Now that is going to be the last video solution, but I'm sure that you looked at the, if you're clicking on this one, I'm sure you looked at the written solutions and were like, wait, he's just summarizing a movie. Like, what the heck is that? Like, that's ridiculous. Like, what is the movie? Does he even title the movie? I don't think I do. Maybe I do at the end. I remember watching that movie when I wrote those written solutions out a couple of years ago. It was probably pretty similar to this time of year as well. Probably pretty close to New Year's. And so you're like, oh, okay, well, geez, I just don't want to do my own thinking. It says write in your own words, but I don't want to do that. So why don't I just watch the video solutions and source his words? Well, yeah, that's a good idea. That's a good way to sort of beat the system. Except I'm not going to do that. Nice try. Instead, what I'm going to do is, I wanted to do like a Rickroll, but I'm not going to. I've already done that. I've already been there, done that. Instead, what I'm going to do is I'm going to tell you a different story. So basically, the story of my New Year's. So last year, in 2023, on New Year's Eve, effectively, pretty much all of the people that I hang out with, all of my good friends, were all still in Elk Grove, save for one who was in Florida at the time. But most of them were all there, so basically we decided to go out for dinner, as we always do. And each year I do that, I always leave a really big tip. I'd been going to Five Guys for several years and leaving large tips. I think the largest I ever left was $200, just as kind of a nice gesture, because Five Guys is important to me, all those different things. So in 2023, all of us went to first Five Guys, they were closed. Then we went to Mike's Diner, they were closed. So we ended up at Black Bear. And then we came back to my house, and we were going to do our little mystery gift exchange, or Secret Santa, and then play cards or something for a while until New Year's. Well, the power went out, so we played Uno in the dark. It was not a good idea, but it was kind of fun in that weird kind of giddy way, and we made it all the way to New Year's. There was still no power, if memory serves, but it was cool. It was a great thing. Well, this year, 2023, going into 2024, I guess I'm not saying the year's correct, so this would have been on December 31st, 2023. One of those friends reached out to me, and I hadn't been in touch with him for quite some time. He'd had some medical issues pop up, and he'd been up and down from Southern California, Northern California, and we just hadn't connected. Effectively, we hadn't connected in 365 days. Which is wild. I mean, I guess, okay, one time, we went to one of those friends' birthday parties, so we saw each other, but we hadn't, had much of a conversation throughout the entire year otherwise. And that friend reached out to me and just goes, hey, do you want to get dinner? And I'm like, yeah, sure, it sounds good. I didn't have any plans with anyone else, because two of our friends were in Europe, They got super cheap tickets, so they went to Europe. And the other 2 friends had moved over the course of 2023, and they were doing something out there with some of their friends and their housemates. But he didn't know that. Like, my friend that texted me didn't know that. So basically, he then sent me a message and said, "Hey, I'm going to ask if everyone's around, like, and just kind of check. Is that okay?" And I'm like, "Well, yeah, of course, that's fine." But I knew the answer was going to be no. So he texts everyone, and a couple hours later, he hears back and goes, "Yeah, no one's around." And I'm like, "Well, that's okay. We can still go to dinner." So he and I went and got dinner and did the exact same thing. We went to Five Guys. They closed. We missed by 1 minute. 1 minute. They didn't lose as much tip. I couldn't give as much this year because I've been giving to another cause, but beside the point. Then we tried Mike's Diner. They were again closed. It's not because we're dumb. I think both pretty smart people. We just basically were trying all the same things because these are restaurants that we prefer. Then we went to Black Bear and did all that stuff. And effectively that was going to be the whole night. It was just like the 2 of us instead of like 6 or 7 of us like it normally would have been. And I had told him that I wanted to go to bed early. I always go to bed early. And I get up really early, so that just kind of works with my schedule. But as we were leaving, it was like it was a really good time. I hadn't seen him for a while. I mean, for 365 days, give or take 1. And so I just thought, well, hey, what I was going to do is I was going to go home and like work on something on my computer for an hour or an hour and a half and watch my favorite movie one more time. Favorite movie is Past Lives. I saw it in theaters 5 times in 2023, and I've watched it, I think, now 3 or 4 times on Blu-ray, or technically it's on streaming because I bought it and added the digital copy. And I love that movie. Like, it gets me every time. It's awesome. If you haven't watched it, watch Past Lives. And so anyway, I said, well, that's all I'm going to do. Do you want to do that? Are you up for that? And he's like, yeah, that sounds good. So basically, we came back to my house, and for an hour and 48 minutes, I think that's how long Past Lives run, not counting the credits, I worked on the project that I was working on my laptop, and my friend watched the movie on the couch. I mean, we both were watching. Said almost nothing to one another, save for like one line in the middle. There were a couple funny lines. Obviously, we laughed, and then I got choked up at the end because I always do. It's a great movie. And afterwards, he stood up and goes, "That's a great movie." And then I drove him back to his house and gave him a hug and went home and fell asleep at like 10 o'clock. And so that was my New Year's. Why am I bringing this up? 1, it's to burn you for trying to get out of explaining in your own words the whole plus C thing. But really, I wanted to point it out because it was one of my favorite outcomes. Like, out of everything in 2023, it was cool that that was the last thing that happened. And the reason for that is this. I didn't see my friend for almost an entire year. And it wasn't like I didn't see my friend, but we were in constant communication. We weren't. Like, we weren't. I didn't reach out to him even one time, and he didn't reach out to me even one time. Not in a malicious way, because that's not what happens. Like, adult friendships just kind of go that way. Sometimes you just don't, like, connect or cross paths. But in any event, on the very end of the year, at the very last possible thing, that friend reached out to me. We got together for the first time in effectively 365 days. I think that's safe to say. That he and I specifically chose to do something together for the first time, and it was like no time had passed whatsoever. And it's an odd thing to say because I think we tend to be a little bit more insecure about our friendships, and I'd say that about myself for sure. And we tend to think like, oh, you've got to maintain it. You've got to like work really hard. It's a relationship of sorts. You've got to work to make it work. And yeah, of course that's true. But something that I've learned as an adult, and I think I have to qualify myself as an adult now that I'm 37, and that's for a couple more months only, is that yes, that's true. Like, you should do that, and obviously, like I would prefer to spend more time with my friends. It just doesn't always work out that way. But the important thing to note is that as you get older, there's so much infrastructure underneath those relationships. As in, you've spent so much time together, you've grown close, you've gone through the ringer together, you've done all sorts of things together, and effectively, that stuff doesn't disappear. It's not like it just goes away, just like, poof, gone. It's just like, no, it's always there. Like, you know that. And yeah, there's something that's, sort of disappointing and sad about the fact that, I don't see all of my friends all the time. But the cool thing is when you get back together, you really can pick things up where you left off because, like, we've done so much together. But the other cool thing is that when you don't get together all that often, there's just a lot of stuff to talk about. There's just, like, a rich conversation. Like, my friend and I had an entire year's worth of stuff to talk about. And while that isn't perfect, like, that isn't the perfect world scenario, because we would have talked about probably something anyway, it is nice to remember. And I say that because the people that are taking this class that might potentially be clicking on this video, and I'm not sure anyone will watch, if anyone watches like leave a comment. Maybe leave the comment like past lives, or leave a comment like Black Bear or something like that. Something that will tell me that you actually watched this part. Because I'd be curious if anyone ever does. I suspect no one ever will. But I think it's a nice reminder to realize that as you get older and as you move past Franklin High School and wherever else that you're going, and you start to like look into the future, you start to think, you get that insecurity of like, oh shoot, I'm not going to see my friends. They're just going to abandon me. Like, we'll never be close again. We're just not friends anymore. Yeah, that could happen, but like also it might not happen. And that I think it's helpful to be reminded that yes, work on things. Yes, stay in touch. There's so many ways to stay in touch. Like, that, you know, me and this friend it just was rare. Like, we're both that kind of person that don't reach out that way. But it doesn't have to be the end of your relationships and your friendships and all those things. So just wanted to put that out into the world. And also, like I said, I'm freezing here, and this is my way of burning people, but like burning them in the most earnest and positive manner that I can possibly think of, an optimistic manner that I possibly can. So just know that's something that I think is valuable to remember, is that yes, you should try to work on your friendships and relationships and make sure that they stay there. But just because you get separated for a while or you don't see each other for a long time does not mean that you can't come back together and find a familiar spark and like connection and closeness. Actually, during the pandemic with the class of 2021, so this would have been in 2021, I had a student share that during Therapy Thursday, in fact. I know exactly who the student is. Obviously, she's not watching the video. But I remember, because I was right here. I was literally right here when that happened. Different computer system and everything. But I was right here because it was on Zoom. We were on Zoom at that time. So I think it must have been quarter 2, actually. So 2020 or 2021. And that student shared that sort of concern, that frustration, that concern, that worry, that like, I'm afraid that when I leave, I'm going to lose these friendships, like we're going to grow apart and we're not going to see each other, we're not going to connect. And what I told her, and what I told the class, because that's how Therapy Thursday works, was that, yeah, that happens sometimes. Like, yes, like I can absolutely attest that out of all the people in high school, I'm in contact with like sort of one. There's some friends that I got close to online that were from other classes, so technically we went to high school together, we didn't know each other. Like, I am going to the wedding of my like elementary and middle school, one of my closest friends, like the person whose house I slept over at all the time. I'm going to his wedding in February, but I haven't seen him since 2019. Like, these things just kind of happen. So, like, yes, it is possible that you will just like grow apart and never see each other ever again. But on the other hand, it is possible that when the opportunity strikes, you will be instantly pulled back together. And what I told her was that to think of it as like magnets. And like, yes, not every single person's friendship, or not every friendship or relationship can be like that. But for many of us, like, because of all that infrastructure, like, you've sort of grown attached to one another. And although you can pull those magnets apart, let's make sure I can get myself in a little video here. Even though you can pull those magnets apart, that doesn't mean that they aren't able to come back together once you get close. And it's just one of those nice things to remind myself. Like, my closest friends, like, yes, they're in Europe right now, and like my best friend has a daughter who's, I think, turning 3 this year. Oh, that's crazy, don't think about that. She's turning 3, and my other friends have moved to Rancho Cordova, whereas I used to be able to just like text somebody and go, hey, do you want to go get Peony Palace? And it was easy. And that's a scary thing. Like, scary isn't maybe the right word. I don't think I'm actively scared of it like I am someone walking into my house and just kind of hiding in the closets, moving from room to room while I'm not looking. That's a fear. It's just kind of like, it's scary in the sense that like you worry that things will change, because they are going to change, and that's a scary thing. You want the good things to stick around. That's kind of the goal, is like keep the good stuff around. But I really liked that my 2023 ended with a good reminder about just how effectively magnets can work. And in that case, that me and a friend that hadn't seen each other, saw each other one time across 365 days, but hadn't really been in contact for 365 days, just instantly, when given the chance to like get together, magnets. So, in conclusion, I did not talk for 1 second about the whole plus C thing. That's on you. I mean, I guess I did throughout the video, honestly. But I shared a positive story, which is something that I told myself that I would do at one point anytime I filmed video solutions, and then I just didn't, because you get like self-conscious and you're like, nobody's going to watch this. And you know what? I don't care. If one person watches this, I have succeeded and made this worthwhile. And I wasn't exactly dying to do this video solution project today. I really don't want to do any more work, but it feels more worth it when I do something like that, to be honest with you. So, yeah, hopefully you watch this. Hopefully you watched it all the way through because you were curious what story I was going to tell. And if you didn't watch this, well then I'm not even talking to you. So yeah, do whatever you want. But yeah, I'm going to call it a day right there. So thank you for watching. If you're hearing me talk about this, you must have watched the last section. So again, yeah, leave that comment. Like, leave the comment I said. That'll tell me something. Maybe there'll be a prize for it. But yeah, thank you for watching. I hope this was helpful. The video solution part. But really, honestly, like, I don't really care if that calculus part was helpful. I'm doing this for my OCD. I do care if the magnets analogy is helpful. I would love if the idea of that could be something that kind of adds something to the way you look ahead in your life, the way you think about relationships. If it helps you not write one off that you thought might need to be written off, then great. That's what I hope. So yeah, this was about plus C and antiderivatives and indefinite integrals, but it's also about magnets. How? If you're just clicking on the very end frame, you'll have to go back and watch 13. So yeah, I'm going to stop now. It is Tuna Fish Tuesday, and I'm going to go enjoy that and watch something on YouTube probably. So yeah, thanks for watching. Goodbye.